Okay, so we talked about there's like infra-bandits, infra-RDPs, infra-RDPs, all of those thingies. We talked about, like we say that there's a notion of learnability in the grad for informationism. So what's like the relation? So for classical theory, we know that like if H is the class of all, communicating entities even, we haven't explained exactly what are communicating entities, but we can sort of guess. So RDPs or even entities with like learnable class, right? Well, I haven't really explained what a communicating RDP is, but basically it's kind of the same thing. It's like, there's some policy from every state to get to every other state, so it's essentially the same thing. So those classes are learnable. The same thing is kind of true for the infra case. So infra bandits is certainly learnable, and then communicating infra RDP or even RDP is still going to be learnable. And here we need to kind of explain what does it mean to be communicating. So notice that it was kind of implicit in my talk earlier, but if you compare what I've been talking to in this lecture to the talk where I was talking about reinforcement learning theory, then it's kind of like everything we talk about here, it sort of corresponds to the lifelong learning setting, right? You can always kind of embed the episodic learning into lifelong learning by just making your environment reset to the initial state of every episode. So you can kind of regard it as special, as like this. Episodic is a special case of the lifelong. But kind of the native setting is the lifelong. And that's why we need the communicating condition, right? Because it's lifelong. So what does it mean for an infra-RDP to be communicating? Well, there's actually different ways to generalize it. So first of the most obvious way is that one condition we could write is that, like for any states, there exists some policy pi such that for any co-policy sigma, the probability of with respect to sigma pi of visiting S2 if we start at S1, where this probability is this is the simplest way. In other words, this thing is saying that we can we have a policy that forces transition from S1 to S2, no matter which policy we're playing against. So sometimes we kind of, the whole information thing, I haven't said it, but you can think of all of it as a zero-sum duplication, right?
Sorry, can you repeat?
I think informationism in general, you can always think of it in terms of zero sum two-player game. Because your decision rule is an accident. Whereas you're doing accidents, it's kind of like a zero-sum game. So it's like you choose the policy, the opponent chooses the co-policy. So we sometimes call it upon a Murphy, in order of Murphy's law. That's somewhere trying to follow in class. So in infra-RDPs communicating where you can kind of go from any state to any other state, no matter how Murphy tries to stop you from doing that. But this condition is actually kind of too strong. We can do some weaker conditions. For example, we can do resettable infra-RDP. So resettable means that if we do this condition, but only for S2 being the initial state. So resettable infra-RDP means that for any S1 and S,
well, if the initial state can get anywhere, then can't you just compose things, or?
1 second, let me write it down. For all co-policy. Probability. Starting from 1. Right, so this. Sorry, so no, it's just there's no S2 anymore. So if we did S0, initial S0. So, okay, what's happening here? We're saying that from every state, it's possible to force going back to the initial state. So, why we didn't have this thing for the unambiguous case? Or I say something and this might answer your question. Unless I misunderstood the question, then you can ask it. So in an unambiguous case, this condition doesn't really add anything new because, well, some states it's not possible to reach. They're not influencing anything anyway.
Mm-hmm.
But it's like, so if all the states are reachable, so first of all, we can only consider the case in which all the states are reachable because there are some unreachable states, they're kind of not doing anything, so we can just throw them out, right? Once we consider the case where all the states are reachable, it means that from any state we can go, from the S0 we can go to any state. If from S0 we can go to any state, and from any state we can go to S0, it means that we can go from any state to any state.
Mm-hmm.
So, in the unambiguous case, when we have an RDP where all the states are reachable, then resettable is the same as community. But in the ambiguous, in the infra case, it's not the same. Why? Because what does it mean that the state is reachable? It might be that there are some states that are reachable, but they're only reachable with Murphy's cooperation.
Mm-hmm.
So we cannot throw the states out, because maybe Murphy will just will help us reach the states and then we'll reach them.
Mm-hmm.
So what happens is that you can, with Murphy's cooperation, you can go from S0 to any state. Without Murphy's cooperation, you can go from S0 to any state with Murphy's cooperation. So it means that there exists some policy and some co-policy. You can go from any state to S0 without Murphy's cooperation. So there exists some policy such that for every co-policy. Those two cannot be composed to argue that you can go from any state to any state without cooperation. It does imply that you can go from any state to any other state if Murphy wants to help them. But this is not. But this would be a weaker condition that's not sufficient to apply learnability.
Mm-hmm.
Okay, you're following me?
What is the last one, sorry? Like,
so again, so we have this condition of communicating, right? And now we define a new condition of resettable.
Yeah.
So I think that in the unambiguous case, which is just normal like reinforcement learning.
yeah, I agree that they're the same if it's everything is
Yeah, okay. But in the infra case, they're not the same.
Okay.
And the reason they're not the same is because,
So we should define reachable. If we define reachable as the second,
so we define reachable as the first thing here.
okay, then it won't be the same.
Is that
Shouldn't
there
we define
exists
this as-
a policy and a co-policy, or is that exists a policy such that for all co-policies?
Here it's
Both are
exists a
exist.
policy such as a policy. Here it's exists a policy such as for all co-policies.
Okay. So if there was a for all by the co-policies, if at state 0, for any target state, there's a policy
Yeah.
that's guaranteed to get there,
Yeah, if any state
then
was,
could you compose them?
yeah, if any state was strongly reachable,
Hmm.
then we could compose them. But this condition is too restrictive. Like, why consider only? I mean, there's an obvious reason why in the unambiguous case we can always assume without loss of generality that all states are reachable. And we shall just not doing it.
Mm-hmm.
But here we cannot assume without loss of generality that states are strongly reachable.
Right. Another one is, does anything in particular change when you swap out probability of 1 for expected time steps is finite?
Right. So, no, I think that nothing, I'm almost certain that nothing changes.
Okay.
Yeah. I mean, for the unambiguous case, I'm certain that nothing changes. For the infra case, I'm almost certain that nothing changes.
All right.
Okay, but so and then the fact that can argue that even just resettable so resettable infra-RDP also form a learnable class. Yeah, I think what I meant to say is I meant to say finite. Over here. Because if it's not finite, it adds more problems. So finite means that the state space is finite. Yeah, and then I think your question is true. If you don't have the finite, then I don't think it's, or maybe it's still bounded, but it's not uniformly bounded. Okay, I don't know. But I'm not sure actually what happens if you want finite, but for finite, yeah, and then it turned out that this condition can be relaxed even farther into something which I call quasi-communicating infra-RDP, think I won't go into the exact definition right now. But there might be an interesting problem here to try to understand what's the most general condition in some sense. So all these conditions have the property. Okay. Another thing is that I was kind of glossing over something here. So I said that the class is learnable, right? But to say that something is learnable, I need to specify what the utility function is. Okay? I need to specify what the utility function is. So, like when you're talking about just RDPs, and usually the utility functions it seems to be there's a reward function, which is a function just of the observation. But here I'm currently in a setting where I'm like, we could do that. So certainly those learnability claims are true for reward functions. So recall that the reward function was a function of from distance to 0, 1. Okay? So one option is to have this be some function that only depends on the last observation, right? Have some r in 0 from O to 0, 1, and then we can just define r of h as r of, really should be a better notation. This some time, but a0 of 0 in n of n, this will be just r0 of n. So this is one option. But you can also do a more general thing. And the more general thing would be to consider reward functions which are themselves defined by a finite state machine. Right? So what does it mean? It means that, it means that we have, so there's a notion of, we can call it reward machine. Reward machine. So what a reward machine is? So a reward machine has a state space, initial state, a transition function in the reward function. And the way it works is, the transition function tells you, given a state, an action, and an observation, what the next state is. So that's like in an RDP. And the reward function is just some function which assigns to every state some number. Okay? And now this reward machine, like if I give you a reward machine, it defines a reward function like this. Right? Because I could say that the reward associated with this machine of history h is equal to this r capital applied to phi m of h. So phi m is the state representation, same as so if you fix a finite reward machine, so if you take, for example, resettable finite infra-RDPs, then this will be learnable for any finite reward machine. So it's kind of a nice class in the sense that not just it's learnable for some very specific utility function, but some very broad class of different utility functions.
Is it possible to like integrate the reward machine into the RDP itself so that?
Oh, sorry, the reward machine needs to be also communicating for this to be true. So if we have, right, so this is learnable for communicating reward machines. Because if not communicating, then yeah, that's bad. So here communicating just means that you can reach from any state to any state somehow.
Yeah, I'm wondering if it's possible to put the reward machine inside of the RDP and just have like the R0 which depends on the last.
Yeah, I mean this is the point. It's like you can, given a reward machine in the RDP, you can construct like a bigger RDP where the reward would only depend on okay, there are some details that so what does it mean for a reward machine to be communicating? It means that we can reach from any state, any other state, but assuming that observations are chosen adversarially. Okay, this is what it means. So in other words, so in other words, given a reward machine, we can construct an infra-RDP by making the observation kernel be just equal to the top. So knowing the top and t look the same. With the right top like this or something, or whatever. T like this. Or maybe I just write the word top. Prove it. Top of O. So the top is like the cradle set, which is the entire delta O. Okay. So given a reward machine, I can add an observation kernel which is completely like this is observation kernel which produces which is like completely unconstrained. So it says given a state and an action, you can see any observation at all. It's a complete maximal ambiguity. And then we can call the reward machine communicating when this infra-RDP is communicating. And actually, it's enough for it to be resettable, probably. Yeah. Yeah, pretty sure it's actually enough for the reward machine to be also resettable. So, and like I said, resettable is not even the most general condition. There's something called quasi-communicating. And yeah, and it would be kind of interesting maybe to just as another kind of small research direction to kind of try to understand where we can say what's the most general condition in some sense. It's kind of a little hard to formalize because it's like yeah, I mean, well, I guess you could try to do something like fully classify all. Yeah, I guess what you could try to do is, for example, try to classify all classes of infra-RDPs, finite infra-RDPs, that have the property that this class is learnable for all resettable reward machines. It could be a cute research question, I think.
Is the reward machine just a general part of the definition of RDPs, or is it specific to the infra case?
A reward machine you can also do in the unambiguous case.
Okay.
Absolutely.
Sorry, can you paraphrase reward, like why I mean reward machine?
So reward machines are like a tool for specifying utility functions. Okay, like we want to be able, and the thing is that it's kind of like in classical reinforcement learning theory, you usually see something like a reward function, which is a function of the state, for example. it already assumes a particular state space. Which is annoying because the state space should not be should be dependent on the hypothesis, it's kind of related to what I was saying about learning state representation. There's no God-given state space. So we want, and this is also why we want RDPs. So we want everything to be phrased in the language of actions and observations, and not tied to some specific state space. And in this framework, we have this notion of hypothesis and utility functions and learnability. That's what I kind of explained in the preamble part before going to the information. Right? We have environments, and there was a notion of hypothesis class as a class of environments, and there's a utility function, or a reward function, and there's a notion of what does it mean for a class of hypothesis class to be learnable, and so on. So now when we go in this framework, studying what are some natural examples of learnable hypothesis classes, right? Then we need to learn. So the notion of learnable is relative to a reward function. So we also need some way to naturally specify reward functions. And reward machines are one way of doing this, which is nice precisely for the reason that kind of Yarki said, that it allows us to kind of use the kind of classical machinery of state dependent, of reinforcement learning where we think in terms of fixed state spaces to get learnability results in this framework. So this is just a very, very natural way to specify reward functions, basically. That's all.
So I didn't get a chance to think about it once. If you incorporate that into the original thing to make it another process that has a normal reward function, does that stay quasi-communicating, or given that this is resettable?
So if you take an RDP and a reward machine, you can in some sense combine them, particularly the product of the state spaces, right? And you get then a reward. Well, the reward doesn't depend on observations here; it depends on the state. But I mean, there's something slightly tricky going on here in the sense that here the reward depends on the state, not just on the observation, right? But we could. Oh, okay. Let me rephrase it like that. What we could do, given the reward machine, we could extend our observation set to include the state space. So given a reward machine, I could define a new observation set, which would be defined by O times S, where S is the F of the reward machine. Okay, let's call it S R, so you remember the first two reward machine. Why? Because it's the reward machine is just fixed. I don't need to learn it. I already know it, right? It's just my interpretation. Someone told me. So because it's fixed, I can always compute those extended observations. Right? I see a stream of action, observation, action, observation, action, observation. And I can augment those observations into observations in this space by just applying T to compute the state here all the time, right? I get some mapping from A time O star to A time O hat star. This is just some canonical mapping that depends on psi r, whatever, It depends only on the reward machine, which I'm not. Now, once I did that, if someone also gives me an infra-RDP, I can construct a new infra-RDP. So given an infra-RDP, I can construct a new infra-RDP where the state space is equal to the old state space times, or, no, actually I don't even need to, do I even need this, or can I just stay within the same, no, I do not, right? Because otherwise I don't get. Okay. I can also extend the state space like this. And now I can define the observation kernel, the extended observation kernel, to be, so this is like, so this state now consists of two parts. There's like the original state, and then there's like the reward machine state, right? And there's some action. So this I can just do by, I take my B of SA, and this gives me, so this thing lives in box O, but I want something new. So I will just, okay, actually writing all the notation out explicitly is going to be a little pain. But I mean, it's obvious that given such a set of distributions, so, okay, so maybe let's, so given any observation, I can feed it into the transition kernel of my reward machine to get the next state, right?
Mm-hmm.
So I can do something like, it will be,
So my high level question is just like, are we requiring that this be resettable so that because the proof does this combination and then the resulting RDP has like some property,
so we want this.
which is what still is communicating.
Yeah.
That's just what I want to do.
Okay, so maybe, I don't know, if this is an access, so we can write it out, but there's like a way to just combine the reward machine and infra-RDP to get a new infra-RDP whose reward function only depends on observations. And then like,
Yeah, fair enough.
yeah.